So, electrode potential. This is a value that allows us to compare two half cells to see which is going to become the positive electrode and which is going to become the negative electrode when these two half cells are connected. It also allows us to see which direction the equilibria will go in and predict whether test tube reactions will take place or not. We can also use it to calculate what's known as the electromotive force of an electrochemical cell. This is basically the potential difference of a cell measured in volts, and the reason why it's equal to the potential difference of the cell is because a high resistance voltmeter is used to measure it. It's measured using a standard hydrogen electrode. This is the standard reference electrode. I'll have a go at drawing it here. You will have a, hang on, let's get the pen. You will have a half cell, which is essentially an equilibria set up between two species. In this particular case, it's a little different to the ones that we've considered before, in the sense that the equilibria is actually between some hydrogen ions and hydrogen gas. Now, obviously in this case, this means that we don't actually have a solid to behave as the electrode. So what there is platinum here. So platinum is used as it's unreactive, and it will actually catalyse the equilibria between the hydrogen ions, which will be present in solution, and these will have to be a concentration of 1 mole per decimetre cubed, and the equilibrium between this and hydrogen gas, which will be coming through here. Now, this will be connected to another half cell, whatever it may be that you are wanting to find the electrode potential of, and this will be a high resistance voltmeter there. The hydrogen gas will be bubbled into the solution, so this hydrogen gas here will be bubbled into the solution of the hydrogen ions, and the equilibrium will be set up. Now, the direction that this equilibrium will go in will depend on what this half cell is here. There are standard conditions that need to be considered when using the hydrogen electrode, the hydrogen reference electrode, which we'll now have a look at. So the standard conditions for measuring electrode potential are a pressure of 100 kilopascals, a temperature of 298 kelvins, and a concentration of 1 mole per decimetre cube. Now, with regards to the standard hydrogen electrode, this concentration is of the hydrogen ions. So if, for example, you are using H2SO4 to provide those hydrogen ions, because this is diprotic, rather than using 1 mole per decimetre cubed sulfuric acid, you would actually need 0.5 mole per decimetre cubed of your sulfuric acid in order to provide 1 mole per decimetre cubed of hydrogen ions. It's important to keep these conditions, these standard conditions, because by altering the standard conditions you can alter the position of the equilibria, and this will have an effect on the electrode potential. This would in turn mean that you can't compare the electrode potentials, which we'll have a look at in another couple of videos' time, and we wouldn't be able to put the standard hydrogen electrode as having the electrode potential of 0.00 volts. So this is the standard electrode potential for the hydrogen reference electrode. This is what this means here. This is standard, excuse the writing, electrode potential. Just to finish off, we'll consider how we would write the convention for this particular half cell. Now, when we were looking at zinc in an aqueous solution, and we were considering the half cell where it's in equilibrium with solid zinc in the equilibrium with a solution of its zinc ions, it was relatively straightforward. We had the zinc solid, we had a line there to show that it was in a different phase to the aqueous ions, so then 2+, and that was aqueous. Now it would depend whether this were going to be the negative or the positive electrode as to whether your salt bridge would be on this side or not, and in this particular way that I've written it here, it would have to be on that side. However, with the standard hydrogen reference electrode, we don't have solid hydrogen, so we've got aqueous ions in equilibrium with hydrogen gas. So we had to use platinum as the electrode so that it could conduct the electricity through the circuit. So in this particular example, what we would have to do is include platinum in our convention. So we put platinum here again. I'm assuming that it would be on the left hand side, and the salt bridge is going to be over here. So here we would have platinum there, and in this particular example, this is suggesting, because its salt bridge is on the same side as it is with the zinc, and the zinc was going in that direction, so in direction of oxidation, that again this one would be going in the direction of oxidation. So what we would have next is actually the hydrogen. So we'd have a line here, we'd have the hydrogen, which is a gas and obviously is in a different phase to the solid, and then this would be going to the hydrogen ions, which are aqueous, so we have again a different phase here, and we would have the H+ ions there, which again is in a different phase to the gas, so we have a line here again. Now if this were to be on the other side, so this was going in the other direction, in that direction, we would just reverse the whole thing. So you would have H+ ions first, then you would have your line, then you would have the H2 gas, then you would have your line, and you have the platinum electrode right on the end.